Okay, we're live. Nice. Good. Awesome. Okay, I'm going to be glancing over there. I don't know if I like that. Okay. All right. I'm definitely going to come up with some sort of like little frame or something for this. It's like a coming up and like a we'll figure out different things to do. Eventually I'll use streaming software. All right, so it looks like I'm started. Okay. I'm starting these streams at 3. I'm almost positive school doesn't actually let out until 3:30. I'm going to check the bell schedule. Regular schedule. Yeah, exactly 3:30. And then when it looks like Wednesday's let out at 2:30. Okay, so I very well may change these hours. Maybe I'll even change them next week. My wondering with these was, were there going to be students at the end of the school day who might have an opportunity to, leave whatever they're doing early, and my hope was sort of a slow roll in for me. So I'm not just in here and boom, there's a million people. I mean, that's ambitious of me. But anyway, when there aren't people in here, just to have something on the stream replays, and so people can sort of get a sense of who I am and how I do. There's other things I can work on, and I'm excited to work on, that will probably come up organically as we're answering questions, but sort of evergreen ideas that are gonna be helpful for everybody at pretty much every level of math things like that, things that we'll probably talk about, I'll probably go through multiple times, which I like. That means I'm going to refine my process. Should probably learn some math jokes and stuff too. This screen that I'm sharing here, this is Miro. You can see Miro up in the corner there. It's a online collaboration space. It's a online whiteboard, which I use when I'm tutoring students one-on-one. This is one of the, actually here, hold on, my batteries are, let's try this. Yeah, and my plan is to start sharing the link to this so people can go in and just browse around. It'll be like a read-only link. Maybe even allow people to leave comments. We'll have to see. We'll experiment. Give me 1 sec. All right. So I think I have myself more or less set up here. Actually, what I want to do. Nice. Okay. It's a little strange to do this to no one. Something I like to talk about as a way to illustrate one of my favorite parts of math, which is that there are multiple ways to do pretty much anything in math, except for maybe the most basic things. But even there, I would imagine there's probably multiple ways to conceptualize it or present it, even if there maybe aren't totally different methods. Anyway, we largely teach fraction division one way. In Oregon, as far as I can tell, I think West Coast, I think all of the US more or less teaches it this way. It's definitely taught this way in CPM, College Preparatory Mathematics, which we'll be talking about on this stream, I'm sure. They go through a whole process of teaching this this giant one or big one, which is a fine concept, and I don't dislike it. It's a lot of process to go through to ultimately lead to what I'm going to call the classic. So, how do you divide fractions? Well, if you've gone through probably the US education system in the last couple decades, your answer, if you even remember, is probably flip and multiply. That's basically everybody's response. And then they can say it, and then oftentimes they don't remember how to actually do it. And there's a lot of reasons for that. This is not a good method. I mean, it's a fine method. It does the job, and it's fast if you know what you're doing, but it's not a good method to learn how you divide fractions. It doesn't teach you anything about dividing fractions. It's a process. It's a trick, and that's going to be one of the large themes here is tricks are fine if you know what they do, if you know why they work. We don't like tricks if they obscure the math, if they're just a way to get from this part of a problem to this part of the problem and have this mysterious place in between where something happens and you know it's right. We don't like that. You can flip and multiply if you know why and how, and we'll even talk about why and how. But it is not where we're going to start. Instead, well, let's really quick. Well, yeah, it's not where we're going to start. There's a lot of confusing things about it. What do you flip? Why are we multiplying? I thought we were dividing, right? There's all sorts of confusing things about it. So the way I multiply fractions, the way I teach dividing fractions is to divide straight across. If you've recently gone through fraction arithmetic, reviewed it or have used it, or you're just really strong on it, this straight across, that might sound really familiar. This is the same way you multiply fractions. Same for multiplying fractions. Oh, we gotta follow. You're not following me. There we go. Excuse me. All right. So we're actually going to use the same method for multiplying fractions, and that will hopefully make some sense when we get a little bit deeper into this. Since there's still nobody here, I want to back up and let's just talk about the context, the justification for my straight across method before I even show it. Because then when I do show it, it'll just seem natural. It'll make perfect sense. I hope, is my hope. So, okay, let's go all the way back. We need a different question. Let's go back to how do you add, subtract fractions? We're not going to go into right this moment why this is the method we use, but we can and almost certainly will cover that here at some point. This will be if the only thing any one person ever gets out of this is feeling a little bit more comfortable with fractions, then that's great for me. Okay, so the way you add fractions or add or subtract fractions is first you need, step one, find a common denominator. All right, we're already getting into some vocab. Let's give ourselves an example to play with, right? Let's add together 1/2 plus 3 plus 2/5 plus 3 fifths. That's fine. We want to add those together. So we need to find a common denominator. This is the bottom of this is the bottom number. And that is to say, we just need a number that is divisible by both 2 and 5, because we're going to convert these fractions. We're going to do sort of the opposite of simplifying the fractions. We're going to go the other direction. We're going to make them not simple so that they have the same number on the bottom. So we need a number that we can multiply 2 by to get some number and 5 by something to get that same number. There's all sorts of ways to do this. The easiest way, it's not always the least common denominator, which you might have heard of, but notice I didn't say least common denominator. I just said a common denominator. Easiest way to do that is just what number do you get when you multiply the denominators? 2 times 5 is 10. So our process here is, I don't want to do this. So 2 times 5 equals 10. So that's our common denominator. I promise you all my handwriting will get better as I keep doing this. I'm a little rough, a little rusty after having not done much writing, much digital writing over the summer. All right, that's our common denominator. So how do we use it? How do we found it? So actually, let's even make that step 2, right? You can maybe think of these as this part, steps 1A and 1B, but let's just call it step 2. Convert fractions to common denominator. Okay. So we need to take our problem, which is 1/2 plus, or rather, actually, we need to take each of these fractions. And we need to convert it so that the bottom number is a 10. Well, we can't, when we're converting fractions, we need the fraction we convert this to also be equal to 1/2, right? 1 out of 2 is 1/2, but 2 out of 4 is also 1/2, 3 out of 6, right? There's lots of fractions that are just a more complicated way to write 1/2 using bigger numbers. And so what we do is we can multiply top and bottom. Oops, where'd my pen go? There we go. Multiply top and bottom by the same thing. You might recall anything over itself is 1, so we're just multiplying 1/2 by 1. This is sort of the big one they talk about in CPM, which means you multiply anything by 1, it doesn't change value. 1/2 times 1 is still 1/2. Actually, we're getting into, I don't want to use fraction multiplication because we haven't talked about it yet. So hold on, we can do this a different way. See, this is what I mean. You can do things in math lots of different ways. So if the bottom is 10, we want this to equal something with a 10 on the bottom. So what's half of 10? Well, it's 5. So that's pretty straightforward. 3/5. We also want to convert that. So we want this to be a 10. So if we break 10 into 5 pieces, there's 2 in each piece. 2, 2, 2, 2, 2, right? And we want 3 of them. 1, 2, 3. That's 2, 4, 6. There we go. So that's 6/10. All right. And now we're going to go ahead and add converted fractions. Oh, actually, I left out a word. Add numerator. Converted fractions. Keeping the common denominator. Why do we only add the tops and not the bottoms? It's a very good question. I do want to go into it more in depth. It's definitely a topic that is worth us spending some time on, because you can understand it. You can understand why this is actually kind of the only way that makes sense. Or you can understand why it would make sense that you combine the tops but not the bottoms, why we treat them differently when we're adding. Okay. So what that says is we should be doing 5 plus 6 over 10. Add the numerators, keep the common denominator. A really quick reason why that is, the denominator tells you how many pieces you're breaking the whole into, but it doesn't tell you how many of those pieces you actually have. It's like a unit, right? The 10th is how big the pieces are. This is saying we have 6 of them. The 10th is how many pieces you've broken a hole into, and this is how many you actually have. So when you add these together, you don't do 10 plus 10. You haven't suddenly broken your whole into pieces that are 1/20th. They're still 1/10 sizes. You have 5 of them, and you have 6 more, so you have 11 of those tenths. And there we go. That is our answer, 11 tenths, which is an improper fraction, they would call it. That doesn't mean it's wrong. So back in elementary school, they may have had you convert this to 1 1/10, but we could also write it as 1.1, all sorts of things like that. That doesn't really matter. These improper fractions are going to be the most useful way for you to work with fractions. So I would just get comfortable leaving them like this. If the instructions say to convert it to a mixed number, which is what this is, go ahead. But in high school mathematics and college mathematics, they never will. Mixed numbers are used in very, very few places in the real world. Baking and cooking is one of them. I'm sure there are a few others. But in most real life industries that rely heavily on math, if they're using fractions, they're using improper fractions. And then decimals only are usually only used if it's an exact decimal, or if you have some level of accuracy you care about. Let's label these. This is a mixed. Oh, no, it's not a mixed number. That's our improper fraction. This is a mixed number because it mixes non-fraction numbers not written as a fraction with numbers written as a fraction. And we don't like this when we're doing mathematics. Like, we don't want to actually put this in an equation or anything, because typically in math notation, one number beside another implies multiplication, but 1 1/10 is actually 1 whole plus 1 more tenth. And so, yeah, mixed numbers are actually kind of a confusing notation when you try to combine it with other mathematics. Anyway, 11 tenths, we got there. we don't have anything to compare this to. This number doesn't actually mean anything to us. It was just something for us to practice these steps on. Subtraction is exactly the same process. You find a common denominator, you convert the fractions to the common denominator in in any way that gets you there. You could use the way we did here. But then instead of adding the numerators, you would subtract them. Subtract the second one from the first one in the same order they're written, right? Keep the common denominator. It's all the same. And for the same reason, the denominator tells you how big the pieces are. The numerators tell you how many you have. And so you figure out, oh, I have this many and I'm taking away this many. Typical subtraction stuff. We didn't define the numerator here, right? This is the top number. I'm going to try to throw things like this. Numbers in blue, those are labels, vocab words. Sometimes I'll throw things in this light blue and then throw them in some sort of box or something. Those would be good things to maybe throw in your own personal notes to have reference to. Or things that you should, if you're not going to be able to use notes on quizzes or an exam, things that could be good to commit to memory. Teachers ask you to, are really forcing you to memorize stuff, push back against it. Forcing memorization on students is kind of ableist, and it's not how anything's done in real life. And memorization is a poor substitute for learning. So just, I don't know, say all of that, push back against if teachers tell you can't use notes and things like that, because in real life you can always use notes. The internet's probably going to exist forever now, and we'll probably always have access to it. So at least usually when it counts. All right. So that's how you add subtractions. And then, as I mentioned, here, I'll put it down here as well, just as a little side. Subtraction uses same common denominator process. All right. In addition to subtraction, I think with fractions are at least I think seem more straightforward than trying to make sense of what it means to multiply or divide by a fraction, right? When you're adding or subtracting, you're just like, well, I have this many pieces of a whole, and I have this many, and I'm either trying to take some away, or I have some other pieces of a whole. I'm trying to combine them together and just figure out how much I have total. So what we figured out with this is that if you have half of a whole, so if you have a piece and it's 1/2 of some whole thing, so half of $1 or whatever, and you also have 3 things that you each know is 1/5 of a whole, so 3/20ths of $1, which are groups of 2 dimes, I guess, but whatever. Which is kind of like what we did here. If you have half of a whole and you have 3 1/5 pieces of a whole, or a piece that's as big as 3 1/5 pieces, and you want to know how much you have total, well, what you have total is 11/10ths of a whole. So you have a whole, and you have one more piece that's the same size as if you broke that whole into 10 pieces. So you have a whole and 1/10. You can tack them all on and make it just one big block, or have your whole and then your one extra little piece. It doesn't matter. It's all the same thing. All right. So let's look at, let's ask the question then, how do you multiply fractions? And so remember, if you feel like this is going a little fast and you don't feel like you necessarily understand the why of adding and subtracting fractions, that's not what we're actually focused on. What we're focused on is dividing them. It might seem like we're doing that a little backwards. But given that we add them by finding a common denominator, combining the numerators, either via addition or subtraction, because the numerator is how many pieces of the size that the numerator tells you, right? That's our idea. So how do you multiply fractions? Well, this one's pretty straightforward. Oh, let's give ourselves a practice problem, shall we? Or an example problem. Let's do 2/3 times 7/10, let's just say. Multiply straight across. Numerator times numerator denominator times denominator. All right, what does that look like? It looks like 2 times 7 over 3 times 10, which equals 2 times 7 is 14, 3 times 10 is 30. Now, the implied rule when working with fractions is typically that we're going to reduce the fraction that we get at the end, mostly for simplicity. Again, in real life, nobody's ever going to hand you two fractions and say, can you multiply these for me? And then that's the end of it. And the fractions don't mean anything. Numbers always mean stuff in real life. They measure things or they tell you, yeah. So 14/30, that's great. So let's think about what we figured out. Actually, let's reduce this, like I said first. The way we can reduce this, similar to how we reduce something like 5/10, right? We say, 5 goes into 5 once, and 5 goes into 10 twice, and we get a half. So we're sort of looking for numbers that go into both pieces, right? And we can, again, this is something we can, and I hope to spend some of this, like, it's kind of why I'm starting the sessions a little early before school lets out, so I can have a little time to do this, maybe as a warm-up for myself, or just have some background content out there for people to reference. So yeah, so there's going to be lots of time to talk about these, each of these little details. And please, let me know which of these things you would be most interested in, the things that you struggle with the most, or the things that are important to you right now, that sort of thing. Okay, so 14/30, then what goes into 14? Well, 2 goes into 14 7 times, and 2 goes into 30 15 times. Excellent. So 7/15, and that doesn't reduce any further. Nothing goes into 7. It's a prime number. And so that is our answer. One step. There's sort of two little substeps: multiply the numerators, multiply the denominators, but like that doesn't seem worth separating out into separate steps. Here, let's make this a different color because this was just like a little example off to the side. Boom. There we go. Just to remind us how fraction simplification works. Let's just throw it way over there. Okay. Let's talk about what we just figured out. The fraction 2/3 times 7/10 equals the fraction 7/15. Sure. Okay, if I say so, right? So 2/3, you have something that's, you have a whole, you break into 3 pieces, and you either have 2 of those pieces or you have something that's as big as 2 of those pieces. Same difference. Now, what it means to then multiply that by 7/10, and this is what it always means to multiply by a fraction, even if you're multiplying a whole number, is how much would you have of a whole? Fractions are always out of a whole. They're never out of some other size. They're always out of one whole. How much would you have if you reduced this 2/3 to 7/10 of itself, right? So this seems to contradict what I just said. We're talking 7/10 not of a whole, but 7/10 of 2/3. But 2/3 is the size of the whole that we're taking 7/10 of, right? That might seem confusing. Well, that's okay. We'll keep sort of talking about it. But that's always what it means to multiply by a fraction, is to, so just as an example, hopefully a slightly more straightforward example. If we wanted to, multiply, let's multiply 8 by a half. Now, this is a mathematical statement that we would probably say in English using words differently to find the result of this. What this means is to find what half of 8 is. How much is that? If we were just to ask somebody for this number, we would probably ask them to divide 8 in half. Not by a half, but divide 8 in half. Divide it in halves, and then tell me how big one of those halves is. And that's what it means to divide by fractions. Find how much this portion of this number is. I'm going to put that in it. How much is 1/2? Actually, I'm just going to write it underneath. This is the same thing as asking, how much is 1/2 of 8? It's the same thing. And the answer is 4. And it's similar no matter what we do. We could do, let's do 12 times 3/4. What we're asking, in English, we would say, how much is 3/4 of 12? So we would break 12 into 4 pieces. 12 by 4 is 3, but we have 3 of those pieces, so it's 9. That's what it means to multiply by fractions, is to find that fraction of whatever the number is multiplying it. So we just figured out that if you were to take something that's a size of 2/3 and you were to break that into 10 pieces and take 7 of them, those 7 pieces would be the same size. So notice the 7 here. Those 7 pieces would be the same size, though each of those 7 pieces, that's what I was trying to say, each of those 7 pieces is 1/15 of the whole thing. When we initially did it, another way to say it, though, is if you take 7/10 of 2/3, what you have is 14/30. You would have to break the whole into 30 pieces and take 14 of them, which would be the same size as breaking into 15 pieces and only taking 7 of those. Essentially, these pieces are twice as big as these. Okay. That's multiplying fractions, and you multiply straight across. And the process of multiplying straight across does this for us. It's very nice, convenient, that in order to find a fraction of some other value, you can literally just multiply the numerator numbers, how many pieces, and multiply the denominators, the size of pieces, and it'll get you there. And then oftentimes, whatever fraction you get, while it is correct, we can still reduce it. And we often want to, if everybody's working with as reduced fractions as possible, then we always know if we're talking about the same fractions or if we're not talking about the same fractions. 14/30 and 7/15, if somebody's looking at those side by side, they'd probably be able to pretty easily tell if they were the same fraction. But imagine these numbers are much more complex. This is a 5-digit number. This is a 7-digit number, right? This is an 18-digit number. There's a 35-digit number. Like, are those the same fraction? that would be much harder to tell. All right. Okay, so let's review, because now we're getting to it. Now we're getting to the fraction division, and I appreciate you sticking with me and going through this justification. You always could skip forward right to how I show you to do the fraction division because it's very straightforward. But I want it to make sense. I don't want to just give you another trick. I want you to feel like you understand what you're doing when you're doing fraction division this way. Like you're working with the fractions, not doing a math magic trick, because math is not magic. Math is rational, explainable, replicable. Yes. All right, so let's review. How do you add subtract fractions? Well, first you want to find a common denominator so you know you're working in the same size pieces. Then you add together the numerators because that's how many pieces you have, or you subtract them if you're doing subtraction. So common denominator, add numerators, keep your common denominator. And addition and subtraction work the same way. Addition and subtraction are inverses of each other. So they should, no matter kind of what system you're working in, they should always work very similarly to each other. Multiplication and division are also inverses of each other, and they should often work in complementary ways as well. So with fraction multiplication, we multiply straight across. That's very straightforward. It gives us the fraction of the first value, the value that represents the second fraction of the first fraction's value. So if we're going to move into fraction division, and you forget everything you know and you just think about what we just went through, it seems logical to me that when we ask the question, how do you divide fractions, our answer should be similar to how do you subtract fractions, which is the same as multiplying. But surely dividing fractions can't be done by dividing straight across just as simply as fraction multiplication. Or why would they have spent all this time teaching flip and multiply, and why would CP/M devote like an entire chapter to justifying this giant one, which is useful for other things, but like is mostly there to support teaching flipping as a way for students to kind of justify flip and multiply. In fact, you can. Same as multiplying. Yes. Okay, let's give ourselves a sample, an example problem, and test this on. Let's see. Let's do 9/16. And we are going to divide that by 3/8. And now what I'm telling you is that you can do 9. I use a division sign. This would be the same thing as 9/16 divided by 3/8. Remember, fractions and division are actually the same thing. 3 divided by 8 is 3/8. So what I'm telling you is that we should be able to do 9 divided by 3 over 16 divided by 8. We get 3 halves. Let's do that on a calculator, shall we? 16. I'll show you what I'm doing in just a sec. There we go. There's my calculator result. 9/16 divided by 3/8 equals 3/2. What does fraction division mean? What does it mean to divide to take 9/16 and divide it by 3/8? Well, similar to how we gave ourselves a simpler example. Let's think about what it would mean to take something simple like 3 and divide it by 1/2. Well, to even make sense of that, hold on. Let's take something even simpler. Let's take 10 and divide it by 2. What does that mean? We know the answer is 5. What does it mean? It means if you take 10 and you just say divide it into 2 equal pieces, how big are they? Well, they're 5. Or if you take 10 things and divide them into 2 groups, how many would be in each group? 5. Things like that. Or if you took 10 and divided it into groups of 2, how many groups would you have? You'd have 5. So similar thing here. If we take 3 of something, dividing by 1/2 means if we took 3 wholes and we divided them into groups that only had 1/2 of a whole in them, how many groups would we have? Or yeah, that's probably the best way to think of it, because thinking about it the other way is a little bit weird, but we'll talk about it. So yeah, if I have 3 wholes and I wanted to separate them into groups that only had 1/2 of a whole in each group, well, if I have 3 wholes, I need to break them all into halves anyway to get those halves. Well, how many halves will I have? The first one will break into 2, and then 4, and then 6. So it equals 6. The other way to say it is, how many times does a half go into 3? How many times does 2 go into 10? Right? That's the more straightforward way. But that relies on talking about multiplication. But 2 goes into 10 5 times. How many times does a half go into 3? How many halves are there in 3? Well, you have a half, and then you have 1, and then you have 1.5 and 2, and 2.5 and 3. You have 6, right? So that's what we're doing. We're dividing. So what we said is we have something we took a whole, divided it into 16 pieces, and we have 9 of them, or we have something that is the size of 9/16 of a whole. And we said, okay, but what if we had 8th size pieces and we had 3 of them? How many groups could we make? Or yeah, if we took those 9/16 size pieces and put them into groups where each group only had 3/8 of a whole. This becomes a lot harder to sort of process in your head, thus why we have tricks and things for it, right? And why we offload it to that. And yes, fraction division does become a little complicated to think about, but remember, it is always the same idea as this. If you understand why 10 divided by 2 is 5, you also do understand why 9/16 divided by 3/8 is 3/2. It's just a little harder to explain this because it has so many more pieces. It has literally twice as many pieces, right? All right. There's some of you may have noticed that I chose awfully convenient fractions here. 9 is perfectly divisible by 3. 16 is perfectly divisible by 8. But that's not always going to be the case, right? And you should be asking these questions of your teachers in class as well, right? When you notice that the example problem they do is awfully convenient, and you're wondering, well, I know the homework problems, the numbers aren't going to work that nicely. So what do we do in that case? Ask that question. It's worth exploring in class time, and it's a good question to have. So our question is, what if the numbers aren't so convenient? Oops. What if the numbers aren't so convenient? All right, let's give ourselves a different fraction. Can I get Google to give me 4 random numbers? I'm just doing 4 random numbers, 1 to 10. There's numbergenerator.org. That seems great. We got 5, 6, 9, and 3. 5, 6 divided by, well, 9, 30. That's not going to work. That's just a 3. Let's get another 9 sevens. Boom. There we go. Okay, this is a weird one, right? Just right off the bat, even just in trying to interpret it the same way we interpret the other ones, you have something that's 5/6 of a whole, and you want to know how many groups you can divide it into. If each of those groups had 9 sevenths of a whole, which is a whole, and 2 more sevenths, right? So this isn't even a full group. So our answer should be less than 1. I guess so. If we go up here and we explain this, you have 9/16, you divide them into groups of 3/8, you can make 3 halves, or 1.5 of those groups is what we figured out. Okay. So I'm saying you should be able to divide straight across. So we should be able to do 5 divided by 9 over 6 divided, 6 divided by 7. That's a decimal, though. We don't want decimals in our fractions. That's not how we're supposed to really do things, right? Like, it's not wrong, but it's not what we're after. We can always write it as 5/9, 6/7, and, well, that's just 5/9 divided by 6/7. That's just a different. That's just a different fraction division problem. So maybe this method doesn't work. It works sometimes, but if the numbers aren't convenient, it doesn't really work. So it'd be nice to have a better method that always works, right? And flip and multiply does always work. This method also works. If the numbers aren't convenient, then step 1 is find a common denominator, which is something you already do when you're adding and subtracting fractions, right? Hopefully it feels at least a little intuitive. It makes some sense that could be useful somewhere else. And yeah, you can totally find a common denominator. So, all right. This is like, what? What's going on there? So we're going to take our 5/6. Divided by 9/7. And I said, I had mentioned easiest way to find a common denominator is just multiply the denominators. And so we get 42. Cool. I'm actually going to tighten this up. I'm going to make it I'm going to say find and convert to a common denominator. There we go. Find and convert to a common denominator. Okay, so 42. So 5/6 needs to equal some number of 42nds. Easiest way to do this, what did I multiply 6 by to get to 42? I multiplied it by 7. Oops, you can't probably hardly see that. I multiplied it by 7, so we'll also multiply the numerator by 7. Now that we've talked about fraction multiplication, this is kind of the most straightforward way to do this sort of conversion. That's 35. Okay, and then we'll do the same thing with 9/7. In order to turn it into 42nds, well, we multiplied the 7 by a 5, so we'll also multiply the 9 by 5, which is 45. And so now we can do 35 over 42 divided by 45 over 42. And now these numbers are bigger, but now we can divide straight across. So you could always find a common denominator first, so you don't ever have to worry about whether it divides nicely. Like, you know, some people struggle to tell if numbers can divide nicely just in their head, and that's fine. So if you just always convert to a common denominator, then you're never gonna have to worry about it. You will oftentimes have to reduce the final answer, but you're probably gonna have to do that. Like, you probably have to do that 80% of the time anyway. So divide straight across. So we're gonna do 35. Oops. Divided by 45 over, and actually when I write this, hold on a sec, when I write this, and this is how I'm often going to write division kind of going forward most of the time, this division sign does not hardly get used in like actual like practice. So I'm going to write this as 35 over 45 divided by 42 over 42. And now notice this nice thing that common denominator did. What is anything divided by itself? How many times does 42 go into 42? It goes in once. 35 over 45. We haven't reduced this. We'll get there. And now we have this fraction divided by 1. But what's anything divided by 1? Well, it's just itself. So it doesn't matter that this is a fraction. Anything divided by 1 is itself. And there we go. We divided those two fractions, and we got a single fraction as a result. We can reduce this. What goes into both 35 and 45? 5 does. They end in a 5. They both end in 5, so 5 definitely goes in. 5 goes into 35 7 times. 5 goes into 45 9 times. And we get that 7/9. And we can check it. I'll check it. I ain't afraid. What were our original fractions here? 5, 6 divided by, oh wait, hold on. Okay, so 5, 6 divided by 9/7. Oh, and let's convert this to a fraction. Let me show you what I got. Let's see, 5, 6 divided by 9. I'm making sure I typed this in correctly. Because I got something different. I got 35/54. I did my math wrong somewhere. Hold on a sec. This is a good opportunity. This is fantastic, actually. This gives us a chance to practice checking our work. This is great. Okay. Let's make sure I kept the numbers consistent throughout the whole thing, right? That's the first thing to check. 5, 6 divided by 9/7. Okay, that's what we're working with. 5, 6 divided by 9/7. Okay, here's what we do. 6 times 7. That's definitely 42. Oh. Ha, here it is. Look, we found it. I said I multiplied by 5 to get 42. No, I didn't. I multiplied by 6. That's so silly. Okay, so here's what we do. Luckily, I can just, on this digital thing, I can just come through and fix this. So this is supposed to be 6 over 6. 6 times 9 is 54. Hey, look, we found that 54 we were looking for. And 6 times 7 is 42. Okay. So this is going to be 54. And then, so if we go down here, 35 over 54, right? Because we do 35, you just try to divide straight across. 35 divided by 54 and then 42 over 40. That all stays the same. $54, and those don't reduce. Only thing goes into 35 is 5 and 7. And all that goes into 54 is 3s and 2s. And there you have it. You can divide straight across even if the numbers are wonky. Indeed, indeed. I devoted a whole hour to that. I think it was worthwhile. I'm checking for submissions, see if anybody's... I haven't seen anybody pop in. All right. So that's fraction division. In this explanation is also kind of a way to understand the flip and multiply, but like I said, it doesn't emerge as naturally. This isn't to say I don't do flip and multiply. I do. It can be very fast. It can be faster to do flip and multiply in your head than to do this, especially because it can require a common denominator. But there is a streamline here, right? So notice right here, right? Once we converted to a common denominator. So the whole purpose of converting to that common denominator is so that if we did it without converting the common denominator, right, nothing divides nicely, so you end up with this fraction in the denominator. So you just end up with two different fractions divided by each other. Here, we still end up with that, except we forced, by choosing a common denominator, we know the bottom numbers, when they divide, they're going to have to equal 1. So the result will literally always be the first numerator divided by the second numerator. That will always be the answer here, and then you might reduce it further from there, right? Let's do another practice, and let's use that, right? Let's do... Let's do 6 25ths divided by let's do 7 15ths. This will work nicely. Okay. So we could try it just off the bat without doing the common denominators first. We'd get 6 divided by 7, which doesn't divide nicely, and 25 divided by 15, which doesn't divide nicely. When you're doing your homework, and if you're here working with me, unless the thing you're working on specifically, your teacher specifically said, try to do this without a calculator, which sometimes happen, and listen to that. Your teacher's trying to get you to do a specific thing. But generally, I'm fine with, if you're not sure if 25 can be divided by 15, if that doesn't strike you one way or the other, have a calculator up, throw it in. If we do that, we get 1.666. It's a decimal, so it doesn't go in evenly, which means we end up in that case for our very first practice one, where we just end up with other fractions. So we do need to do the common denominator. Again, we could multiply 25 times 15. I happen to know, I chose these numbers, so this is convenient, right? that both 25 and 15 both go into 75, which is smaller than 25 times 15. So it'll make our numbers a little easier. But if you don't know that, you can just do 25 times 15 and just work with the big numbers. So I'm going to use 75 as our common denominator. 25, and actually let's go ahead and throw our... So to get to 75 from 25, I have to multiply by 3. So I have to multiply the top by 3 as well. So this will be 18. And so all we're figuring out is that 6/25ths, another way to write that is 18/75ths. Those two numbers, those two fractions are at the same place on the number line. They're just different ways to write the same thing. The same way you could say 10, or you could say 2 times 5, or you could say 7 plus 3. It all means the same thing. You're probably saying it differently than just 10 for a reason if you are. Similar here. 6/25ths is the simplified fraction. 18/75ths is not simplified, but it's going to be convenient for trying to combine it with the 7/15ths. All right, so that 7/15ths then, I said 15 also goes into 75. It goes into 75 5 times, so I can multiply the bottom by 5 to get 75. So I multiply the top by 5. That's going to be 35. And I'm going to double check these because this is where I made an error last time, right? 3 times 25 is 75. 3 times 6 is 18. Cool. 5 times 15. 5 times 10 is 50. 5 times 5 is 25. 5 times 7 is 35. Very good. Okay. I feel confident about that. Now we can take these and we can say 18 over 75 divided by 35 over 75. And now, though, instead of doing 18 divided by 35 over 75 over 75, 75 over 75 is equal to 1. Anything over 1 is itself. Because we looked at the last one and we can see how we can see this pattern and how it's always going to work out this way. 75 is in fact 1. Anything divided by 1 is in fact itself. So the thing that would have been divided by 1 is 18 over 35. And that's our answer. We can see if it reduces. The only things that go into 18 are 2 and 3 a few times. And the only things that go into 35 are 5 and 7. No common divisors. So that's our answer. So if you take something so if you break a whole into 25 pieces, and take 6 of them, and so you have a little thing that's the size of 6/25ths of a whole, and you divide that into 15 pieces and take 7 of them, those 7 pieces are equivalent to if you had taken the original whole, broken into 35, and taken 18 of those. What does that mean? Nothing for right now. These numbers don't mean anything. It is a little about me, I guess. So this is somewhere, and this will probably make its way to my website. At some point, I do want to write a little bit more in-depth about me thing. My background is in applied math, so I like to talk about what we do with the math, how we use it. That's what I studied. That's what's most important to me. Like, granted, there's a space for theoretical math, and theoretical math, all the work that theoretical mathematicians do is valuable, and some random thing that seemed completely useless, 75 years ago, can just pop up all of a sudden in a modern industry with a modern application. So you never know. So I in no way want to diminish the work of theorists and theoretical mathematicians. I happen to study applied math. The way I studied math in college, the way I focused on math was to learn. I learned these things from a theoretical perspective, right? I learned the theorems and the stuff, but then I also was sort of simultaneously using them to model things or to solve problems and answer kind of thorny, messy questions. That's ultimately what math is, right? Like the world is messy, and there's really no way around that. Math is versatile enough, even though it is a kind of an exact thing. It's versatile enough that it can be used to predict that messiness, and to harness it and to break it into less messy chunks. The messiness of the world is an emergent property. You'll probably hear me talk about emergence other times as well. What that is to say is the messiness of the world is not due to the pieces themselves being messy, but rather due to how many pieces there are and the complexity of their interactions. And what we perceive as messy is really just complexity. And so when I say messy, what I actually mean is great complexity, because there's so many moving parts. Math is great at dealing with complexity. And that's actually what the whole goal of the math you're going through is to try to build you toward. It doesn't seem like math early on is capable of dealing with that much complexity because it's not. Middle school mathematics can only get you so far and can only deal with so many problems. So this is your journey through high school mathematics, as rough as we've made the system. The goal is to get you to a place where you have enough mathematical tools that you can break down the messy complexity of your everyday life into chunks that you can problem solve around so that you can accomplish the things that you want to accomplish. And that's ultimately what this comes down to. Math is a tool for accomplishing the things you want to accomplish. I find it to be a very, very useful tool that has both broad applicability and precise uses. So it's I understand when people say math is magical. I don't like the idea, but I understand that it gives us the feeling. It feels magical. So yeah. So today was building to understanding what I think is a more straightforward, streamlined way to divide fractions, which is useful on its own. But one of the main things I like to use that as an example of is how diverse math actually is. People who don't understand math very well, but like it, will often say the thing they like about math is that there's one right answer and there's one right way to get to it. And by saying that, they show that they clearly don't actually understand math that deeply. They are process focused. For them, there was one right answer and there's one way to get to it because they don't know another way to get to it, and they don't know what another right answer would look like if they were shown one. If it didn't come from their method, then it's not the right answer. In mathematics, though, there are oftentimes many correct answers. Some may be more correct than others, and that all comes down to the problem you're trying to solve. The problem you're trying to solve creates constraints, creates specifications, and so there might be a similar problem that somebody else solved, but their solution may not be applicable to yours because you have different constraints or you have different specifications. And so with mathematics, not only are there different solutions, there are different ways to get to those solutions. And sometimes there's solutions you can't get to with certain methods, but you can get to with other methods. And in fact, this is how advances not only in the field of like theoretical mathematics happen, but in other fields where people take a type of mathematics and use it in a totally new way. They apply it to something it's never been applied to before. They take the properties of electricity and they see that they ought to also apply to the properties of light. And that's how you get somebody like Maxwell creating Maxwell's equations, unifying light and electricity for us, making us understand that this thing that we treat as separate phenomenons are actually different perspectives on the same phenomenon, and different mathematics highlight those different perspectives, and that there is yet a unified mathematics that brings them both together and describes them in yet a different way that shows them as different sides of the same thing. This is going to be a major theme here. There's not one way to solve any one problem. For math class problems, there often is one correct solution that the problem, the book, the teacher, the class is looking for. That doesn't mean that there aren't other viable solutions you could consider, and ask yourself about them, and ask yourself, and maybe even ask your teacher, why is this the correct answer, but this other thing that we can get to in this other totally legitimate, valid mathematical way, why is that not considered the solution? And those are actually the interesting questions. Those questions, that's mathematics. That's what mathematics is. It's not combining the numbers and combining the symbols. That's process. Mathematics is understanding what those tell us, understanding how they get us from a state of not knowing something to a state of knowing something. And that's my goal. Help you understand those steps. Feel like you can use mathematics to get yourself from a state of not knowing to a state of knowing. Seems like as good a goal as any. If anybody did pop in here and I missed them, I do apologize. I was trying to keep an eye on the visitor. But I don't know. I'll continue to tweak my setup here. I never did. No, that's news mark is unread. While I never did get any question submissions, I have had some teachers reach out to me and express interest in integrating this. So we'll see how that goes. I mean, it's very straightforward, right? Like, hopefully students should be able to access this on their school devices. I hope. Which means they should be able to access it from school. They tune in, they submit their questions, I answer them. I'm also looking at, I mentioned this at the top, how do I make these notes accessible to people? They need a place to live on my website, I think. I will also begin linking to them in the video descriptions. I didn't realize there was an additional verification you have to do in order to be able to post links in your video descriptions. It didn't occur to me to test posting links in the video descriptions. So that verification is failing for me. So I do know if I have streams, a month worth of streaming history, that should just automatically unlock the capability, but I would like to be able to post links sooner than waiting a month. So I'm continuing to look into how I can get that to work. But once I do that, hopefully this will just be linked. This Miro file will just be linked in the description, and people can click in and follow around. I know one thing that's going to be a little difficult already is the fact that I write on a different screen than I share, right? So I'm working on a tablet to do and using a stylus so, to make my writing to be able to write more easily. And then I have that Miro board pulled up, and that's why you might see, well, you don't see it right now, but you might notice that there's two people in here most of the time. They're both just me. This one is me on the computer I'm streaming from, so I can share this screen. And then the other person that you see in there, also me. That's me on my tablet where I'm actually writing. What I can do is if I click this here, I can make the one I'm sharing follow the one I'm writing on. But anytime I go to a different tab, oh, it didn't quite do it there. I think I have to, no, I think I have to be, if I'm gone from this tab for long enough, it breaks this follow. So I'm just going to have to get better about monitoring that. But I think I will. Well, I hope this presentation of a different way to do fraction division was illuminating, gives you something to think about, maybe, hopefully, a more reliable, understandable way to do fraction division. Heck, maybe this even helps you. I know we didn't go too deep into it, but even helps you, feel a little bit more confident about fraction, addition, subtraction, maybe even multiplication. We can, maybe my intro week is just fractions, right? This first week, I expect to be slow. Fractions can take a while to explain. So maybe tomorrow I'll start off with just let's make sense of fractions. Let's make sense of it adding and subtracting fractions. This is nice. I've been nervous to do this, but I do think it will become a thing I enjoy. I remember being in high school, being frustrated, just saying, I just want to do math every day. I just want people to leave me alone so I can do math every day. I don't want you guys to leave me alone. I want you guys to bug me with math. That's what I didn't realize back then. There's no doing math alone. But I didn't want people to leave me alone so I could do math with others. Stop bugging me with all the stuff that's not me doing math with people. Anyway, anybody who stopped by, if I missed you, I apologize, but I do appreciate you stopping by. Anybody who watches this afterwards and is continuing to listen to me drone, appreciate it. I'm gonna get out of here. I will see you all tomorrow, same time. We'll do 3. I'll keep doing 3 to 4:30 this whole week. I might change next week, but I might hold it steady next week again, and then change the week after. But we'll see.